चलो स्टार्ट करते हैं. So we were on the non-Newtonian fluids. Okay. So we have covered the types of non-Newtonian fluids, then the basic mathematical model, that is the generalized non-Newtonian model. Okay. So in the generalized non-Newtonian model the category, the first model is the power law model, where tau yx equal to minus eta dvx by dy. Eta is the eta can be represented by m dvx by dy to the power n minus 1, where n and m are the two parameters of the power law model. Okay. Now eta is also called the apparent viscosity. Okay. Now here when you remove the modulus sign, if the shear rate is positive, means the at increasing direction of y velocity is increasing, or at the decreasing direction of y velocity is decreasing, then the dvx by dy is positive. When you remove the sign, it will remain the same. Okay, so the minus sign will be outside the bracket. But if dvx by dy is negative, means when you increase the y, when you increase the y, the velocity is decreasing, then the minus sign will be inside the bracket. Okay, so this is the basic difference. Now in the power law model, if n equal to 1, mu equal to m, so it will show the Newtonian behavior. If n is less than 1, then it will then eta will decrease with increasing the shear rate. That means it will show the pseudoplastic behavior, means the fluid will become thinner. Enough fluid will become thinner when you increase the flow rate. If n is greater than 1, that means fluid will become thicker, and the density, the viscosity will increase with increasing the flow rate. So this is called the dilatant fluid. Okay, these are the example of the flow. Now the second model is the Eyring model. In Eyring model, you can represent the sine h, represent the mathematical equation as sine h tau yx divided by a equals to minus 1 by b dvx by dy. Okay, so this model represents the non-Newtonian behavior. So if tau yx is tends to 0 in this model, if tau yx tends to 0, then this will become tau x by a, and tau yx equal to minus a by b dvx by dy, which is the Newtonian flow. So in the Eyring model, if the shear rate is very low, then this equation will give you the Newtonian behavior. Okay, so it can be shown by this graph. Initially it will show the viscosity is constant, then viscosity is decreasing. Okay, initially it will show the Newtonian behavior, then it will show the pseudoplastic behavior. Now the third model is the Alice model. Alice model is also the 3-parameter model. The Eyring model is the 2-parameter model. A and B are the 2 parameters. Alice model is the 3-parameter model, where phi naught, phi 1 and alpha, these are the 3 parameters. Okay, so here again you have the different limiting cases. If phi 1 equal to 0, if phi 1 equal to 0, then your equation will results to minus dvx by dy equal to phi naught tau yx, or tau yx equal to minus 1 by phi naught dvx by dy. So phi naught 1 by phi naught is the constant which is equivalent to the viscosity. Okay, if phi naught equal to 0, then you will get dvx by dy equal to phi 1 tau yx to the power alpha minus 1 tau yx. So this equation is nearly same as the power law model. Or if alpha is greater than 1, then you will get, and the tau yx is very small, then you will get dvx by dy equal to minus phi naught tau yx. So tau yx equal to 1 minus phi naught dvx by dy. Okay, so in this condition, you represent the Newtonian fluid when the tau yx is very less or very large, very less and very large, or it will also show the dilatant behavior as well as the pseudoplastic behavior. So the Alice model is most generalized model, which will show the Newtonian behavior, dilatant behavior, pseudoplastic behavior, as well as the, again at very high viscosity, again the Newtonian behavior. Okay, so the generally, if you want to represent the mathematical model, the rheological model for the polymeric melt, which shows the all 3 types of behavior, then you have to use the Alice model. So Alice model may be used for the fluid which show the Newtonian behavior at very low and very high shear rate, but non-Newtonian behavior at the intermediate values of the shear stresses. Non-Newtonian might be the shear thickening or the shear thinning. Okay, dilatant or pseudoplastic. Now, the fourth model is the Ranier-Filipov model. The fourth model is Ranier-Filipov model. So these all are the scientists' name who developed this model. Alice, Eyring, and Ranier-Filipov. These all are the scientists' name. So this is also a very complicated model. Here you can write minus dvx by dy equal to, in bracket, 1 divided by mu infinite plus mu naught minus mu infinite divided by 1 plus, in bracket, tau yx divided by tau naught, bracket close, whole square, this big bracket close, then tau yx. This is the Ranier-Filipov model. Okay, so in this model, this is a 3-parameter model. Okay, so the 3 parameters are mu naught, comma mu infinite, and tau naught. Okay, so these are the 3 parameters. Okay, now in this case also we have the very limiting cases. Suppose tau yx is very large. Okay, suppose in the first condition, first case is when tau yx is very large. So what will happen? This term, if tau yx is very large, this term will be very small. Mu naught minus mu infinite divided by 1 plus tau yx by tau naught to square. This term will be very low, and a very minute. So then mu naught minus mu infinite divided by 1 plus tau yx divided by tau naught whole square tends to 0, and if this tends to 0, then you will get minus dvx divided by dy equal to 1 minus mu infinite tau yx, or tau yx equal to minus mu infinite dvx by dy. Okay, so this is again the Newton's law. So the Raynier-Filipov model converges to a Newton's law when you have the very high shear stresses. Okay. Now the second case, if tau x is very small, if tau x is very small, then what will happen? This term will be 0. Tau x divided by tau naught equal to 0 because tau x is very small. Okay. So in this case, tau yx divided by tau naught whole square, because if you take a small quantity and take the square of that quantity, that will become more smaller. Okay, so this quantity tends to 0, and when this quantity tends to 0, then Raynier-Filipov model will convert in dvx by dy equal to 1 by, in bracket, mu infinite plus mu naught minus mu infinite divided by 1 plus tau yx divided by tau naught square multiply by tau yx. This is the original equation. Now this term is equal to 0. Okay, so your equation will become dvx by dy dvx by dy equal to 1 divided by mu infinite plus mu naught minus mu infinite multiply by tau yx. So mu infinite will be cancelled out and you will get tau yx equal to mu naught minus mu naught dvx by dy. Okay, so this is the again Newton's law of viscosity. Okay, so here viscosity is mu naught. Okay, so in Raynier-Filipov model, the Raynier-Filipov model shows the Newtonian behavior at very low shear stress and at very high shear stress, but the viscosity's values are different. So this is the basic difference between the Raynier-Filipov model and Alice model. In Alice model, if the shear stress value is very high, this is the Alice model, minus dvx by dy equal to minus phi naught plus phi 1 multiplied by tau x to the power alpha minus 1 multiplied by tau yx. So in this case, if tau yx is very small, then you will get tau yx equal to minus 1 by phi naught dvx by dy, and if tau yx is very large, then again you will get the same answer. Okay, so the viscosity at the low shear stress and high shear stress viscosity is same. Only the in between you have the non-Newtonian behavior. So when you plot the mu versus tau x or mu versus dvx by dy, you will get the same viscosity at the low shear rate stress range and at the very high shear stress range. In between you have the non-Newtonian behavior like this. And now here again you have the same viscosity's value at the low shear stress range and at the high shear stress range, but in between you have the non-Newtonian behavior. Okay, but if you check the melt flow behavior of the polymeric behavior of the polymeric melt, initially they show this is the flow behavior of polymeric melt. Okay, so initially if you plot this mu versus tau yx, So initially they show the Newtonian behavior, then they show the non-Newtonian behavior, and again they show the Newtonian behavior. But the value of viscosity at the initial range and at the final range, that will be different. Okay, so here the viscosity value is mu naught, here the viscosity value is mu infinite. Okay, so you have the two different viscosity values in the actual condition when you check the flow behavior of the polymeric melts. Okay, so Raynier-Filipov model is best suited for the polymeric melts. Why? Because in Raynier-Filipov model you have the two different velocities, two different viscosities at the lower shear rate shear stress range and at the higher shear stress range. Both models, Alice models and Raynier-Filipov models, both shows the non-Newtonian behavior at the intermediate shear stress ranges and the Newtonian behavior at the lower shear stress ranges and the higher shear stress ranges. Okay, only difference is Raynier-Filipov model shows the different values of the viscosity. Okay, so this model is most suited for the polymeric melts. Okay, so basically this model is developed for the polymeric melts only. Polymeric melts as it shows Newtonian behavior at very low and very high shear stress range but comma, here we will put comma, non-Newtonian behavior at the intermediate shear stress range and non-Newtonian behavior at intermediate shear stress range. Okay, plus the values of viscosity at low shear rate range and the high shear rate range at very low shear rate range and very high shear rate range are different. Okay, so these are the difference between the Raynier-Filipov model and the Alice model. Now the last model is the Bingham fluid model. fifth model is the Bingham fluid model. So this model is especially given for the Bingham fluids. Bingham fluids are the fluids which required initial force to flow. So for initial condition, the simple condition, they behave as a solid material, but when you put some force, they will start to flow. Okay, so it is required some initial force to flow, like paste or gels, gels, jellies. So they are the Bingham fluids. In this model, we can write tau Ix equal to minus mu in bracket, this mu minus in bracket mu plus tau naught divided by inside the mod sign dvx by dy bracket close dvx by dy. Okay, so this is the condition is if tau Ix is the value of the tau Ix is greater than tau naught. The second condition is dvx by dy equal to 0. Second equation is dvx by dy equal to 0. If tau Ix is less than or equal to tau naught. Okay, so basically this model has the two equations for two different conditions. If you plot the model, then you will get this type of graph. Suppose this is the tau Ix and this y-axis is this y-axis is tau Ix and x-axis is dvx by dy. X-axis is dvx by dy, shear rate, and y-axis is tau Ix. So this is how the result will show. Okay, so when you have this value is from here to here, you have the tau naught. Again from here to here, you again have the negative side, again you have the tau naught. Okay, so what will happen when you have the higher value of tau Ix, then it will go in the up direction. If you have lower value, it will go in the negative direction. So the tau Ix, the sign will be the same. Working the basically removal of the mode sign. The rules for removal of the mode sign will be same. If the tau or dvx by if velocity is increasing with increasing the y-axis, then you have to take the positive sign. If velocity is decreasing with increasing the y-axis, then you have to take the negative sign. Okay, so you have to check out from the diagram that velocity is increasing with increasing the flow rate or velocity is decreasing with increasing the flow rate. That you have to check from the diagram. Okay, so if tau Ix is greater than tau naught, then you have this. If tau Ix value is greater than tau naught, then you have this graph or this graph. If tau Ix is less than tau naught or equal to tau naught, then your value is dvx by dy equal to 0. Okay, if you goes from below, you will get the one answer 0, dvx by dy equal to 0. Okay, so this is a type of fluid like paste, and so you need the initial force for flow. Otherwise, the fluid will not flow. Okay, we will also solve the problem related to the Bingham fluids. So these all are the different models used in the. Basically, there are numbers of models. So we have only studied the four different non-Newtonian models, which are the important models. First is the power law model, which is most important model. Okay. Second is the this is the first model. Second is the Eyring model. Third is the Ellis model. Fourth is the Ranier-Filipov model. This is the Ranier-Filipov model. Then fifth is the Bingham fluid model. Okay, so you have to remember all these five models. First is power law model. Second is the Eyring model. Third is the Ellis model, and fourth is the Ranier-Filipov model. Fifth is the Bingham model. Okay, so these models represent the Newtonian flow. Power law model is the most basic model, which represent the either the pseudoplastic flow or the dilatant flow or the Newtonian flow. The Eyring model shows the Newtonian flow at the low shear stress range and the pseudoplastic flow at the medium or the intermediate or the high shear stress range. Okay. Then Ellis model shows the Newtonian behavior at the low and at very high shear stress range, and the non-Newtonian behavior at the intermediate range. But in Ellis model, the viscosities, values of the viscosities at the low and very high shear stress range are same. Okay. Then Ranier-Filipov model, the Ranier-Filipov model shows the non-Newtonian behavior at the intermediate range and the Newtonian behavior at the very low and very high shear stress range. But in the Ranier-Filipov model, viscosities values are different for very low and for very high shear stress range. Okay. Then you have the Bingham model, which is specially designed to represent the flow behavior of the semi-solid materials. Okay, with the Bingham fluids, which shows the solid behavior which are in the solid phase at the very low shear stress, the when the force is very low, and which shows the fluid type behavior when you increase the force. Okay, so the behavior of fluid, they were solid or the phase of fluid that is in the solid phase or the liquid phase, that depend upon the amount of force you are applying on the material. So there are number of type of Bingham fluids. Even the glass is also a Bingham fluid. Okay, but the force required to flow the glass is very high. Okay, so basically all amorphous material in the solid phase are the Bingham fluids. Okay, so like the rubber, you have the paste, James, jellies. These all are the Bingham fluids, or the different type of slurries that are also the example, or charcoal, that is also the example of the Bingham fluid. At the lower shear stress of force, there shows the behavior of solid material, but when you increase the force, it starts to flow. Now we will solve one example. Today's class we will solve only the one example related to the power law model. Okay. So falling film model equation, falling film problem that we have solved in the last semester. That now that problem we will solve with the power law model. So falling film on an inclined surface. Okay. So basically you have an inclined surface. The angle of surface with the vertical plane is beta. A fluid is flowing on the surface as a film. So the thickness of film is constant. Okay, so I will make more accurate diagram. This is the liquid film. Here fluid is flowing on the film. You have already solved this problem. The fluid is flowing due to the gravity. So you have solved this problem by using the shell momentum balance in the momentum transport class. Okay. So first we will put the coordinate system in the diagram. This is x-axis, this is the z-axis. So you have the velocity vz, which will depend upon x. Okay, so the velocity might be the vx, vy, vz. You have to repeat all the steps. So first take the assumption steady state flow density is constant. Here viscosity is not constant because this is the power law fluid. Okay, steady state flow you can take, the end effects are negligible that you can take, and the no slip boundary condition will also be applicable. The only assumption which is not applicable is the Newtonian fluid. Okay, so this is not a Newtonian fluid, this is a non-Newtonian fluid because here we are solving the problem for power law fluids. Okay, so the again same x, y, z and time, that may also depend upon x, y, z and time. That may also be vz may also depend upon x, y, z and time. So you have only the vz. This is the vz which will depend upon x direction. Okay, so vx will be 0, vy will be 0, only vz which may depend upon x direction. This will be 0, this may be 0, this may be 0. Okay, so that you already understand why vx and vy is not there, because there is no reason we assume that fluid will flow in the y direction or fluid will flow in the x direction. Okay, fluid will only flow in the z direction because force is the gravity force which is applied on the system. So the gravity will take the fluid at the downward direction. So because this is a surface, solid surface, so it will flow in the x direction only. Okay, so this is the first step. Then instead of using the shell momentum balance, here we will use the equation of motion. Okay, so I will use the equation of motion. So first we will take the equation of motion. So this is the Cartesian coordinate problem. So we will take the equation of motion in the Cartesian coordinate system. Okay. So these are the three equations for the Cartesian equation of motion in the Cartesian coordinate system. So I will take these three equations in the separate page. Now in these three equations, you have to cancel out the terms which are non-zero. Okay, so first you have to identify the non-zero tau and the velocity. So velocity non-zero is vz, which will depend upon x. So non-zero velocity is vz, which will depend upon x. Similarly, non-zero shear stress is that is tau x z, that is the non-zero shear stress. Okay, now come to this equation of motion. Which terms are zero? Vx is not present, so these all Vx terms will be zero because Vx is not present. Pressure is again not changing in any direction, so this will be zero. Now come to the tau xx, tau yx, tau zx. So here you have the tau xz, not zero. Okay, so tau zx is zero. So these all three terms will be zero. So this will be again zero. In the second equation, Vy is zero. So Vy is not present. Here again dp by dy is zero. Again tau xy is zero, tau yy is zero, tau zy is zero, and gy is zero. So you have only the two terms which are not zero. Vz, which depend upon Vz is non-zero and it depends upon x, and tau xz is only the non-zero term. So in this equation you have to search these two terms only. Vz is not zero, but Vz will not depend upon time, so this will be zero. Here Vx is zero, here Vy is zero, Here Vz is not 0, but Vz is not depending upon the Z. Vz is only depending upon the X. So this term will be 0. dP by dz, pressure is equal in all directions. So dP by dz is 0. Now from this direction, tau xz is not non-zero term. This is 0, this is 0. Okay. Again, gz will be non-zero. Okay. So you have del by del x minus 1 by rho. These two terms are non-zero terms. All other terms are 0. Okay. 1 by rho del by del x tau xz plus dz equal to 0. Okay. So this is your answer. You need not to do the shell momentum balance. You can directly use the equation of motion. You will get the answer. Now you can just rearrange this equation. This equation will become del tau xz divided by del x plus rho zz equal to 0. Okay. Now you can integrate this. Gz equal to g cos beta, because beta is the angle. So the beta is the angle. The gravity will apply in this direction g. So this direction you have the g cos beta. Okay. So you can replace Gz equal to g cos beta. So this equation will become, this is minus tau xz divided by del x equal to rho g cos beta with positive sign. Now just integrate this. You will get tau xz equal to rho g cos beta plus C1. Okay. Now till this equation the problem will be same. Okay. Now because it is a power law fluid, now you have to substitute the power law equation, power law model. If it is a Newtonian fluid, here at the place of tau xz you have to substitute the Newtonian fluid model. Now we will substitute the power law model. So for power law fluid, tau xz equal to minus eta apparent velocity dvx by dy, dvx by dvz by dx, dvz by dx, where
एक्सक्यूज मी सर,
हाँ बोलो
सर ये ऊपर वाली इक्वेशन में एक्स भी आएगा ना?
एक मिनट रुको, हाँ इसमें x भी आएगा, है ना? इसको इंटीग्रेट करोगे तो यहाँ C1 is a constant and here you have the x also. ठीक है. Now eta equal to m dvx by dvz by dx to the power n minus 1, eta equal to m inside the mod sign dvx by dvz by dx to the power n minus 1, where m and n are the two parameters of the power law model. Okay. Now first you have to remove this mod sign. Now how we will check? First I am making the diagram in this page, so you can check that dvz by dx is positive or negative. So this is the x direction and this is the z direction. This is the x direction, this is the z direction. Okay. So when you move in the positive x direction, this is the positive x direction. When you move in the positive x direction, velocity is decreasing. Velocity is 0 at this point. Vz equal to 0 at this point. Vz equal to maximum is this point. Vz equal to Vmax. So when you move in the x direction, positive direction of x, velocity is decreasing. That means dvz by dx is a negative quantity. And when this is a negative quantity, then you can write tau xz. This is equation number 1. equal to minus m in place. Okay, first we will remove the mode sign, then we will write the final equation. Okay, so then you can write eta equal to, so here we can dvz by dx is negative because vz is decreasing with increasing x. Okay, now we will remove the mode sign. Okay, so eta equal to m, inside the bracket you have minus dvz by dx to the power n minus 1. Okay, now this eta value will be substituted in the original equation. You will get now tau yx equal to tau xz, and here you have the tau xz. Tau xz equal to minus m in bracket minus dvz by dx to the power n minus 1 multiply by dvz by dx. Okay, now what we will do, we will take this minus sign with this dvz by dx. So you will get m in bracket minus dvz by dx, because then we have to remove these brackets also. So we will do slightly in the better form, dvz by dx. Okay, this is the multiply. Okay, now you can multiply these two quantities, so it will become m in bracket minus dvz by dx to the power n. Okay, tau x z equal to. Okay, now this is equation number 2. Substitute the equation number 2 in equation number 1. Okay, so here you have to substitute. Before substitution, you can also check the C1. Okay, so first we will substitute, then we will check the C1. Okay, so here you will get m in bracket minus dvz by dx to the power n equal to rho gx cos beta plus C1. Okay, now this m is basically the type of viscosity. Okay, so at vz equal to 0, at x equal to 0, you have the air liquid interface. Okay, so at x equal to 0, viscosity, these value dvz by dx should be equal. Okay, so the apparent viscosity of the eta should be equal to the viscosity of the air, because here you have the air, here you have the liquid. So in liquid you have the viscosity eta at this point, so this eta should be equal to the viscosity of air. Okay, so because viscosity this at this point dvz by dx should be equal, and these two values are equal at this point. So viscosity of these two viscosities should be, because shear stress value is very less in the shear stress values are very less in the air. So this viscosity should be very this term should be very low. Okay, so at x equal to 0, shear rate values, shear rate of liquid and air should be equal. So you can say dvz by dx air should be equal to dvz by dx liquid at x equal to 0, comma, liquid air interface. Okay, so in this condition, these two are equal. Okay, now because these two are equal, the viscosity, value of viscosity of air is very low, then apparent viscosity of liquid. So you can say tau xz at z equal to x equal to 0 should be 0. Okay, so in this equation, if this value is 0, tau xz equal to this value is 0 at x equal to 0, that means C1 equal to 0. Okay, so this tells you that C1 equal to 0. Now your equation will become, suppose this is equation number 3. Now this equation number 3 will become, now from equation number 3, you can write m in bracket minus dvz by dx to the power n should be equal to rho gx cos beta, because C1 is 0. Now just rearrange this equation, you will get minus dvz by dx minus dvz by dx to the power n equal to rho gx cos beta divided by m. Now if you take n here, you will get minus dvz by dx equal to rho gx cos beta divided by m to the power 1 by n. Okay, now you take the minus sign again here and integrate this. If you integrate this equation, you will get Vz equal to under root n rho g cos beta, these are the constant values, divided by m, multiply by x to the power 1 plus 1 by n divided by 1 plus 1 by n plus C2. Okay, so this is the value of Vz. Now this is again a constant, this is again a constant. Now what you can take, you have to determine the value of C2. So for C2, Vz is 0 at x equal to delta, and a no slip boundary condition, which you don't already know, that the second boundary condition is no slip boundary condition where Vz is 0 at x equal to delta, because the thickness of film is delta. This is delta. So just substitute the delta value here, you will get Vz equal to n divided by n plus 1 in bracket in root under root n equal rho g cos beta divided by m multiply by delta to the power n plus 1 divided by n in bracket 1 minus x divided by delta to the power n plus 1 divided by n. So when you substitute the boundary condition, you will get the final velocity. Okay, so this is the application of power law for the Pauli film problem. Okay, so we can solve the second problem also, tube flow problem using the power law fluid. Second is tube flow problem. For power law. So the basic concept is same. Initial steps are same. Basically, you have a tube where fluid is flowing, horizontal tube. We have already solved this problem for Newtonian fluid. Okay, so in the center you have the center line where you have the dimensions. The length of the tube is L. Here you have pressure P0. Here you have the pressure PL. The dimensions are, this is the z-axis, this is the r-axis. So we have already solved this problem using the equation of motion. You have the Vz, which will depend upon r. So the non-zero shear stress is tau r z. This is the non-zero quantities. So you have to take the equation of motion again. Equation of motion for the cylindrical system, because this is the cylindrical coordinate system. So this is the cylindrical equation of motion for the cylindrical coordinate system. Just take this equation of motion for cylindrical coordinate system. So in this equation, Vr is 0. So all these terms will be 0. These all terms will be 0. V theta is 0. These terms will be 0. These all terms will be 0 again, because tau r theta values are 0. Now in this equation, right hand side is 0. Vz is not dependent upon t. Vz is not dependent. Vr is 0. V theta is 0. Vz not dependent upon z. This is 0. dp by dz will be there. Tau rz will be there. These two values are 0. Zz 0 because there is no gravity. Okay, so you have the two equation, 1 by rho del p by del z plus 1 by rho 1 by r p by d del by del r tau rz equal to 0. Now here you have the two quantity. One quantity will depend upon z, one quantity will depend upon r. So basically you can integrate this quantity separately. Okay, when you integrate this quantity separately, this will become P0 by PL. This quantity will become P0 minus PL divided by L. Okay, so just substitute this value here. Here you have the negative sign, so this will become PL minus P0. Okay, just substitute this value here, you will get the final equation. So I am writing the final equation. P0 minus PL, P0 minus PL divided by L minus 1 by R del by R del by R R tau RZ equal to 0. Just integrate this equation, you will get tau rz equal to P naught minus PL divided by 12 R plus C1 divided by R. So at R equal to 0, C1 tau rz is finite quantity. At R equal to 0, tau rz is finite. So C1 equal to 0. So you will get the equation. So you will get the equation tau rz equal to P naught minus PL divided by 12 multiplied by R. This is equation number 1. Now you have to substitute, instead of the Newton's law of viscosity, you have to substitute the power law model. Now again, power law model. The power law model is tau rz equal to minus eta dvz by dr, where eta equal to m in mod sign dvz by dr to the power n minus 1. Okay, now we can check that this dvz by dr is positive or negative. So when you move in the positive direction of r, this is the positive direction of r, this is also the positive direction of r. This is a cylindrical coordinate system, so this is again positive, this is again positive. Okay, so when you move the positive direction of r, velocity is decreasing. The velocity is highest at the middle point and 0 at the solid wall. Okay, so velocity is decreasing when you move the positive direction of r. So dvz by dr is negative. Because when r is increasing, then dz is decreasing. Okay, so you can write eta equal to m in bracket minus dvz by dr, similar to the last problem, to the power n minus 1. So when you substitute, you will get tau rz equal to m in bracket minus dvz by dr to the power n. Okay, substitute this value in the original equation, you will get m in bracket dvz by dr minus dvz by dr to the power n equal to, here you have P naught minus PL divided by 12 R. Okay, now just solve this problem. So just integrate this value, you will get value of dz. Again, first take the m this side, right hand side, then take the open the bracket, you will get dvz by dr equal to P naught minus PL divided by 12 multiplied by m to the power 1 by n multiplied by r to the power 1 by n. So this is positive, this is negative. Now you can just integrate this. This is constant, P naught minus PL by 2 lm to the power 1 by n is constant, only 1 r is variable. So when you integrate this, you will get Vz equal to minus P naught minus PL divided by 2 lm to the power 1 by n multiplied by r to the power n plus 1 divided by n divided by n plus 1 divided by n plus C2. Now you can take the second boundary condition, that is at r equal to capital R, Vz equal to 0. Okay, so Vz equal to 0, then when you substitute this, you will get C2, value of C2, that is equal to minus, in bracket, P naught minus PL divided by 2Lm to the power 1 by n multiplied by capital R to the power n plus 1 divided by n divided by n plus 1 divided by n, and when you substitute the value of C2 in the original expression, you will get the value of Vz after substituting value of C2. In original equation, you will get Vz equal to under root minus under root n P naught minus PL divided by 2Lm R, capital R to the power n plus 1 divided by n divided by n plus 1 divided by n, in bracket 1 minus R divided by capital R to the power n plus 1 divided by n. So this is the velocity profile when you have the power law fluid. Okay. So in this way, we can use the other models also. So power law model is most simplest model. You can use the Alice model, Ranier-Filipov model, Eyring model, or the Bingham fluid model. Okay, so all models can be substituted, and you can, based on the type of fluid, you have to take the appropriate model, and you can determine the velocity profiles as well as the other properties, fluid properties. Okay, this is how we have to solve the problem when you have the non-Newtonian fluid. Okay, this is enough for today's class. कुछ पूछना है?
नो सर।
अच्छा, इस वीक में मैं आगे छुट्टी पे हूँ वेडनेसडे से, तो नेक्स्ट क्लास विल बी ऑन मंडे।
ठीक है सर।
चलो, समझ में आया आज की क्लास में?
यस
सर रिवाइज कर